Hi, my name is Marie Mucci. I work for Michael Hatridge at the University of Pittsburgh. Today I'm going to be talking to you about how I've been using three-way parametric processes in order to make a maser out of Josephson elements. A maser requires a few essential elements, amongst them an artificial atom that I can invert its state, a cavity that I will allow photons to build up in, and a resonant exchange between these two. As has been done in previous experiments, I can let this artificial atom be a transmon qubit. I can drive a two-photon transition from G to F, allow spontaneous decay from F to E, and then resonantly couple that E to G photon into my cavity. A system like this is called a maser ratchet because if I properly engineer my rates in this hierarchy that's shown here, then I can, by indirectly exciting my qubit, I can make sure that photons are continually going from the qubit to the cavity and not the other way around. So I'm constantly pushing into the cavity to let photons build up in it. And additionally, in a system like this, we see a complete erasure of the phase of that initial drive. So the light seen in that E to G transition is really cleaned up in comparison to my initial drive. If I only consider, though, changing around transmon parameters, this is pretty difficult to achieve. So I'm going to introduce a parametric object that I'll have a little bit more control over so that I can achieve masing with that. That parametric object that I'm going to introduce is the snail, or the superconducting nonlinear asymmetric inductive element. The snail on its own has third-order Hamiltonian terms, and the transmon qubit that we all know has fourth-order terms. If I capacitively couple the two, they become weakly hybridized, and in that hybridization, I get third and fourth-order Hamiltonian terms shared between the snail and the qubit. One of those third-order terms that I'm particularly interested in is this GQSS, where you'll see that if I drive my S mode, I gain one photon each in the qubit and the snail. And this two-photon parametric gain process is exactly the process that's going to be responsible for inverting my qubit. And I'm going to explain that a little bit later. And additionally, I get this fourth-order cross curve between the qubit and the snail. So notionally, I could use the snail to read out the qubit. However, this term is fairly small, so that's not possible. And also, the snail does have a fourth-order self-Kerr. However, I can tune my snail to operate at a point where this is fairly close to zero, so I don't have to worry about the snail's self-Kerr pushing my frequencies away from where I expect them to be. So now that I've weakly hybridized my snail and my qubit, I have a new artificial atom. And so in that hybridized system, I have my orange numbers representing state of the snail and green letters representing state of the qubit. If I drive my snail at the sum of the snail's frequency and the qubit's GE frequency at this drive that I call sigma SGE, I apply that drive and I put one photon each in the qubit and the snail. I let my snail decay at the fast rate kappa S, and then I end up in this state here, 0E, that I can then couple that qubit photon with my cavity. Now, of course, higher energy levels of this system do exist, but because the qubit is anharmonic and my drive is only tuned for the qubit's G frequency, I don't have to worry about ever rising up in this qubit ladder. So I stay in this lower manifold that I wish to be in. And also, because the snail is weakly anharmonic, I can start with some number of photons in it. I don't have to start with 0 photons in the snail. So for example, if I was to start here in 1G, I could either very quickly decay into 0G, or if I do successfully put one photon in the snail, I still would very quickly decay to 1E and keep myself moving along towards the 0E state. So this project has taught us a lot about engineering our quantum objects and their coupling rates to the outside such that we engineer the bath in order to push you no matter where you start, to always push you into the 0E state. So now my next challenge is to build it. On a single chip of sapphire, I print a snail and a transmon qubit. This lives inside a copper tube so that I can flux bias my snail, and that copper tube opens up into an aluminum coaxial cavity, and the system is coupled to the outside via 3 microwave ports. And I've included here a photo of the actual cavity where you'll see that this is that opening between the copper and the aluminum parts. There is a large frequency detuning between my qubit and my cavity. So right now, the cavity is just being used for a dispersive readout of my qubit. And another feature that I do want to point out is the lifetime of the snail. I've engineered the snail to be by far the fastest lived object in this system, so that kappa S is the dominating fast rate, pushing me into a qubit excitation state. So like I said on the first slide, my first task is to invert my atom. And I'm going to do that by applying that sigma SG drive. So if I prepare my qubit in the ground state, I want to see the qubit go from G to E. If I had applied no drive at all, and I let the qubit naturally go from G to E, it would do it in over 500 microseconds. However, by applying my drive to the snail, I'm able to make this G to E transition of the qubit in just 0.5 microseconds. And I've included this color plot here to show you that if we vary the voltage of that sigma SG pump and the frequency of it, I show in color the inversion time, this tau GE. So you see there are a fair number of pump conditions that make my qubit's G to E inversion time significantly faster than its T1, than its time to go from E to G. So this system is fairly robust to pump conditions. However, the green star is representing the particular pump conditions that we used in order to get this fastest inversion time of just 0.5 microseconds. So by quickly inverting my qubit, I'm able to constantly keep repopulating it. So every time that I put a photon into the cavity, the qubit is right back in that excited state to keep giving photons to that cavity. And another feature that I do have to point out is the fact that there is this increase in the probability for the qubit to be in the F state. However, this time to go from E to F is the same whether or not we apply the drive to the snail. So it's slightly comforting to us to know that this is a feature that is present independent of the drive that we apply. But it's just a feature that is naturally present. And if you have a qubit in the excited state, there's a non-trivial chance that it's going to jump up to F. So I've inverted my qubit successfully, and my next challenge was to resonantly couple to the cavity. The easiest way to achieve this would be if I was to replace my transmon with a squid so that I could tune the frequency of my qubit to that of the cavity frequency and resonantly couple between the two. However, we said, let's try to do this with parametric drives. So if I look at the fourth order interaction between my qubit and my cavity, I can apply a parametric drive at 2 times the cavity frequency minus the qubit's G frequency. In the stiff pump approximation, I get an effective third order interaction, where at the expense of a qubit photon, I gain 2 cavity photons. And for this to be possible, to see a buildup of photons in the cavity, I need to have the cavity live longer than that E to G transition time. Applying this drive, what we look to see is, can we decrease the time for the qubit to go from E to G by applying this drive. However, on this plot here, as the system is now, we're able to make this transition in 1.4 microseconds. But because the cavity lived 0.74 microseconds, we're not quite there yet. However, we are confident that if we decrease the cavity lifetime, which is an easy fix for us experimentally, then for every cavity lifetime, we see multiple transitions of the qubit into the cavity to let photons build up in it. So moving forward, we are going to achieve mazing one way or another. And we're going to continue exploring how far can we push this system by applying different sets of parametric pumps. And I encourage you to listen to a talk by my colleague Shikao, who's going to be talking about how we can apply similar parametric pumps in order to create an effective photonic chemical potential. And also, I'd like to thank our theory collaborators, and Changshu Liu is going to be talking about in his talk how we can make a system like this operate below the Shavalov-Towns limit for the maser line width. And with that, thank you very much.